Okay, in this lecture I'm going to briefly cover radiotherapy, covering various different treatment modalities and giving explanation as to why we might use a certain treatment modality for a certain type of cancer. So here we're dealing with using radioactivity somehow to treat cancers. And the types of radioactivity that we're going to be discussing is photons versus particles versus isotopes as the thing that we deliver to a patient. Okay, so firstly I'll go through the different types of radiation that we use. So firstly we've got electromagnetic radiation, which is your X-rays and your gamma rays. These are an extension of the electromagnetic wave spectrum. You'll know it more familiarly as light. Just light is the electromagnetic part of the electromagnetic spectrum. X-ray and gamma rays are just very high energy light in effect. And we use this for external beam radiotherapy mostly. We can also use subatomic particles as radiotherapy, so we can deliver something that emits alpha particles by injecting radionuclides directly into the patient. We can have beta particles emitted, so these are electrons mostly. We call that brachytherapy. And then we can do proton beam therapy, so we have an external beam of protons fired towards the patient's tumour. We call that that's part of external beam radiotherapy, but that's specifically proton beam therapy. Your X-rays and your gamma rays are also external beam radiotherapy mostly. So this slide shows the basically what the main types of radiation are. So an alpha particle is 2 protons and 2 neutrons. They have very poor penetration into tissue, so they can penetrate, even within tissue, penetrate about 1/10 of a millimetre, if that. So this comes from a radioactive atom, where a radioactive element would be implanted or injected into a patient. That undergoes alpha decay. The radiation that's emitted is a helium nucleus, so 2 protons, 2 neutrons. This equation here just describes the loss of an alpha particle. So you've got a parent atom, and that radioactively decays into a daughter atom and emits off the alpha particle. That alpha particle goes off and causes considerable damage to any nearby cells. Second form is beta decay, where this is typically loss of 1 electron. So the parent element undergoes beta decay, and you end up with a electron emitted from that original atom. These are relatively short distance, so dealing with less than 3 centimeters, usually 1 centimeter-ish. Now we can have loss of an electron or loss of a positron here. Now these are much less ionizing than alpha radiation. Then finally we've got gamma emission. So this is where the parent element is in some sort of excited state. It will undergo decay and emit a gamma ray. Now, although gamma emission does occur from radionuclides that we may implant into patients, high energy X-ray and gamma rays really come from linear accelerators, which I'm going to talk about later. So we don't necessarily use radioactive elements for radiotherapy that emit gamma. We would primarily use gamma that comes from a linear accelerator, and we'll talk about those later on in the lecture. So as I mentioned earlier, electromagnetic radiation behaves much like light does, in that it travels in straight lines, it travels at the speed of light. It is a form of energy. It does behave like a wave and a particle at the same time, but we don't need to worry about that too much. All we need to know is these are photons, much like light photons, but just much higher energy. Because they're higher energy, they've got a shorter wavelength and a higher frequency. So we're dealing with things that have got a shorter wavelength than ultraviolet. When we're dealing with X-rays, we can have low energy X-rays that are used in diagnostics. And we have a unit of energy for our electromagnetic radiation. So visible light is in the order of 2 to 3 electron volts, whereas your diagnostic X-rays 40 to 125 kilo electron volts. Some therapeutic X-rays, if you're using them for superficial tumours, will be not much above this range, but then when we're doing therapeutic X-rays for external beam radiotherapy for something like an internal tumour, you'd be going up to as high as 20 mega electron volts. These are very, very high energy X-rays, really, really short wavelength. And this is just summarised here by the electromagnetic wave spectrum. We have all of your very long range radio frequency spectrum down here. Microwaves, which are longer wavelength than your visible light. Between microwaves and visible light you've got infrared. As we go through red visible through to yellow, green, blue, violet, we're into the ultraviolet, and we all know that ultraviolet light is damaging to DNA. It's higher energy. When that light is absorbed it can cause damage, and we'll talk about how photons cause damage shortly. And then beyond ultraviolet we're into the X-rays, and then we're into the gamma rays, beyond that cosmic rays, which I'm not going to talk about. So radiation can be either ionizing or exciting radiation. I'll start with exciting radiation. This is where something like a photon is absorbed by an atom, or potentially exciting an electron. The electron becomes excited, it goes to a higher energy state, so it goes from, let's say, here up to here. It then falls back down to its original position, and in the process can give off light or heat, but goes back to exactly as it was before. So that's the basis of things like fluorescence, where a photon of light is absorbed. A molecule will reorganize its electrons, they will go back to where they started from, and they will emit a photon of light in response to absorbing a photon of light. So that's exciting radiation. Whereas in contrast, ionizing radiation is where that photon comes in, excites an electron to such an extent that it leaves the parent atom and leaves this atom charged, and the electron itself is charged. That electron can go out, if it's a very high energy electron, can go and cause the same thing to happen to a nearby molecule, to maybe split that, or cause a breakage of a bond and turn water into a hydroxyl ion and a H+ ion. And then this itself, which has now lost an electron, is a charged particle as well, so that then can react with something else. And these molecules which have been ionized are charged, highly reactive, and in terms of radiotherapy these will then react with anything that's nearby. If it reacts with DNA it will cause DNA damage, and that's the basis of radiotherapy. So the DNA damage that occurs in response to radiation can be direct or indirect. I'll start with direct damage first, and this can be where the radioactive particle passes through the nucleus, hits the DNA, and causes either a single strand break, as shown here, or a double strand break. And something like a helium nucleus from alpha emission can easily pass through a nucleus and cause several double strand breaks if it passes through several bits of DNA, cause lots of damage. And also, as it passes through, can create reactive oxygen species that can also attack DNA. The indirect DNA damage comes about by a photon or an electron coming in, typically hitting a water molecule, because water is the most abundant molecule within cells. So if that photon or that electron hits water, it can split the water open into OH- and H+, and that OH group there can react, if it occurs in close proximity to DNA, that can react with DNA and cause a single strand DNA break. And this is shown in more detail here, so we can see an X-ray photon coming in, hitting a water molecule. Now, as that photon's absorbed and we emit an electron from that atom, you will end up with what we call an ion pair here. So this will create a hydrogen ion and a hydroxyl radical, and these hydroxyl radicals, are extremely reactive. So if this is anywhere near DNA, will bind and cause a breakage of a phosphodiester bond. This will also cause the emission of an electron. That electron can combine with another nearby water molecule. That can split that water molecule into, because it will now become charged, and that will split that into a hydrogen radical and the hydroxyl ion. So what we've got here is extremely reactive species here, here, and here that can all react with DNA, and if they react with a phosphodiester bond of DNA, they can cause a single strand DNA break. So most of the DNA damage that's caused by radiotherapy is caused by this sort of splitting of water to create these hydroxyl radicals, hydroxyl ions, hydrogen radicals, and that's what's causing most of the DNA damage. So when we're talking about radiotherapy, we discuss doses in terms of absorbed dose. So a patient will be exposed to a radiation source of some description, and when we talk about absorbed dose, it's how much energy from that radiation is absorbed per kilogram mass of tissue. So we work with grays, and 1 gray is a joule per kilogram mass of tissue. And this is used in prescribing radiation doses, so that a patient may receive, let's say, 60 grays in 10 doses each of 6 gray, that type of thing. So a patient will be prescribed a certain number of grays of radiation. Now, it says here it's not affected by type of radiation. What actually this means is, if you look at the radiography lecture that is also up on YouTube now, describes this in more detail, but basically because alpha particles per watt of energy absorbed are 20 times more damaging than beta or gamma. So we can have an absorbed dose and an equivalent dose. If someone receives 1 gray of gamma and 1 gray of alpha, the alpha will cause 20 times as much damage. So this graph shows a therapeutic ratio, and it shows in the red line the probability of controlling a tumour with radiation given all of these possible doses, and the blue line represents the probability of causing some sort of complication. That complication could be excessive tissue damage, let's say a secondary tumour formation, and what you want to do is somehow get these lines as far apart from each other as possible. And there are various strategies to do that. You can do some of the approaches of external beam radiotherapy, where we rotate a radiation source around the patient rather than just blasting a patient with a column of radiation that's going to cause effectively an entry wound and an exit wound. If you can focus that on the tumour, then you can effectively give a lower dose of radiation than if you were just bombarding the patient with a cylindrical beam of gamma rays, for example. We can fractionate doses, so if someone was to receive enough radiation to completely control the tumour, let's say here 64 grays of radiation, if you gave that in 1 dose, you'll be absolutely certain to cause local tissue damage. So yes, you might sort out the tumour, but you'd also possibly kill the patient, depending on where you'd irradiate it, but certainly cause extensive tissue damage. Whereas what you can do is fractionate the dose and give that in 10 or 12 doses, adding up to, let's say, 60 grays of radiation, and that helps to separate these two lines from each other. So what you want to do is, if you were to give this dose, you'll be 90% sure of controlling the tumour, but 30% chance of causing some sort of problem. Some of the research that I'm doing at the moment, I might talk about a little bit about this later, is trying to use drugs which are radiosensitizers. So basically allow you to give either a lower dose of drug so that this line shifts to the left, or by giving a lower dose of drug you're effectively having a smaller chance of complication, or possibly by giving a lower dose of a lower dose of radiation with a drug that's a radiosensitizer, you move this to the left, which is the key point that I'm trying to achieve. So the aim is to get something that will give a near 100% tumour control rate, but with a minimal complication probability, and that can be achieved by moving this curve down to the left by having to give a smaller dose of radiation to control the tumour, or fractionating the dose so that a patient can tolerate 6 degrees of radiation, but by giving 6 degrees of radiation in 10 doses, that makes it much more tolerable than in a single dose. So you're effectively shifting the blue line this way by fractionating and the red line this way by giving a radiosensitizing drug, and these are two separate strategies. Okay, so the first form of radiation that I'm going to talk about is radionuclide therapy. So this is where a radioactive element is injected into the patient. In this case, iodine, so iodine-131 is used to treat thyroid tumours, and that's because iodine accumulates within the thyroid, and even thyroid cancer cells take up iodine. So what we're doing here is, if we inject a patient with iodine-131, it will all end up in the thyroid. So this is a patient that's been injected with this, and we're looking at some sort of scan looking for radiation emitting from the patient, and you can see radiation is focused on where the thyroid is, so that shows that it has gone to the right place. So the half-life is about 8 days, so you can give this and the patients will be hot for a while and then cool down. The key point about this is, if the cancer is poorly differentiated, that is, the cells no longer resemble thyroid cells, they will no longer take up the iodine, and therefore the treatment will not work. Now in this particular case, we've got a high sensitivity image here, and a low sensitivity image here. So from this one, it looks like all of the iodine has gone to the thyroid. However, if you take a longer exposure, you can see that yes, there's vast amounts of iodine here, but there's also focal points spread throughout the body, and in this case it's someone with thyroid cancer where the cancer has spread from the thyroid to various places within the body, including the spot there in the brain. Now as long as the cells spread throughout the body take up iodine, this iodine therapy will hopefully control those tumours. So another radionuclide therapy is using radium. This is a bone-seeking radiopharmaceutical. Now radium will accumulate in bone in the same way that calcium accumulates in bone whenever there's bone mineralization going on. It just naturally seems to gravitate towards bone. This is showing its breakdown. There's loads of different isotopes of radium. This is just one of them that decays by emission of a helium nucleus. Radium 223 it should be, undergoes alpha decay in about 11 days. So again, patients will receive this, they will be emitting alpha particles for a period of time, but then the radium will all have decayed, and then they'll cease to be sort of radioactive. However, alpha particles will not get out of the patient's body. The beauty of this radium is it binds to the surface of the bone. In this case, we're trying to deal with tumours that grow on the bone surface, and this is prostate cancer cells. When they metastasize from the prostate, that spread from the prostate, they tend to grow in the bone marrow. So if you've got radium lining the bones, prostate cancers are growing there, and that should kill off the prostate cancer growing in the bones. And this is shown here. This is a whole body scan of a patient with metastatic prostate cancer. So what we can see here this actually it's a bone scan. I'm not going into detail about that particularly, but this black spot here is where the prostate cancer is growing within that patient's vertebra. So what we are wanting to do here is get that radium to the bone, particularly where there's new bone formation, and that black spot is a region of new bone formation. The rest of the skeleton probably won't take up much of the radium, whereas bone that is being actively turned over due to the cancer being present will take up more of the radium, and then we get a very, very short distance emission of alpha particles, because the alpha particles can only travel about 0.1 millimeter. Now we can also tag radium and other radioactive elements to antibodies. So in this case we've got an antibody to a B cell marker, CD20. B cells are a type of lymphocytes, and some B cells go on and produce antibodies themselves. That's myeloma. In this case we're looking at B cells from non-Hodgkin's lymphoma. Those B cells are all CD20 positive. So if you've got an antibody that recognises CD20, CD20 is just the cell surface protein, that antibody recognises the CD20. You've then got a little chemical linker group on here and a chelating group which acts very much like EDTA, which you might have come across in a lab. EDTA chelates certain metal ions. Well, this chelator will chelate in this indium and this yttrium. So the radioactive element is effectively tagged and linked in to the antibody. This antibody will stick to all B cells, and that will eliminate the patient's entire B cells, whether they're normal or cancerous, but that doesn't matter, because we can regenerate some more. But that hopefully will then get rid of all of the tumour cells in the patient. Now, brachytherapy involves implanting a radioactive material into the patient, usually in the formation of small metal seeds. So iodine-125 and cesium-131 are implanted in metal seeds, and in this case this is a patient's prostate. So using a transrectal sort of biopsy type needle, but same idea as I think I talked about transrectal ultrasounds last week, but we can go in through the rectal wall with a device to implant these radioactive seeds throughout the prostate. So every bit of the prostate is no more than about a centimetre away from a radioactive bead, and these iodine or cesium beads are emitting either usually beta emission as the main cause of death, cell death here. So half-life of, in this case, 10 days. So these things will emit radiation for a period of time, and then they will effectively go cold. A plaque brachytherapy is where we actually attach a radioactive implant to a patient, and in this case we're dealing with a patient's eye. There's a rare tumour type that I did my PhD on called ocular melanoma, or uveal tract melanoma, and that's where the melanocytes of the choroid or the ciliary body can become malignant, cancerous, and these have a very high metastatic potential, and about half the patients who develop these tumours die. There's various ways of treating this. You can either just enucleate, that is cut out the entire eye. You can try and cut out the tumour without damaging the eye too much, or you can attach a ruthenium plaque to the sclera of the eye. Now the sclera has actually got is very cartilaginous-like material, quite acellular, and that's very tolerant of radiation. So the tumour is underneath this plaque on the other side of the sclera. So we attach the plaque for, depending on how hot this plaque is, that will depend on how recently this plaque has been made. So when they're brand new, they're really, really hot, so maybe put it on for 2 days. If it's been hanging around, been used on lots of patients and being maybe a year old, it'll be less hot, and therefore you may have to increase the time that it sits on the patient's eye. The time it sits on the patient's eye is dependent on how deep the tumour is, and you want to get, in this case, 130 grays of radiation to the tip of the tumour, which might be here about 6mm from the implant. So all of these things have to be taken into account, but basically you stitch on the plaque, leave it in place, and then remove it a bit later, hopefully when the tumour is dead. So we've got various different ways of killing tumours with radiation. We've got a choice of alpha, beta or gamma. Alpha, very short acting, so you'd want it getting directly, literally sat on the tumour cells. So we can do that with bone seeking radium 2, that should be 223. All the way through this lecture it should be 223, not 233. So you want that bone seeking radiopharmaceutical, or you want something like yttrium attached to an antibody, so that antibody literally sits on the tumour cell, and that is required because it's so short acting. Beta emission has got a maximum range of 1 to 3 centimeters in soft tissues, depends on the isotope and the energy of the electrons given off, but that's ideal for implanting into somewhere like the prostate or doing the plaque brachytherapy. And what we're going to do is move on to gamma, because gamma is very different in that gamma is very, very highly penetrating. So most people will be aware of external beam radiation, where we use a linear accelerator, which is an X-ray generating machine. If you go to the original handouts and click on that link, you'll get a little video clip of a patient undergoing radiotherapy in a linear accelerator, and you'll see how impressive these machines are. Those machines, you have effectively like a cathode ray, and you excite electrons, fire them at a target plate, and that target plate gives off a very well characterized beam of high energy X-rays, which are then delivered to the patient in a shaped beam that matches the shape of the tumour. So this is a CT scan of a patient's tumour. There's the tumour, and what you'll do is fire the beam of rays at the tumour, and the beam of rays can be closed down using sort of lead aperture, and it can be closed down to match the shape of the tumour. So if you irradiated this tumour, you would have a beam of rays that match that shape, but then you rotate the beam around the patient and fire rays from lots of different angles whilst trying to avoid any crucial structures like the spinal cord and the heart and that type of thing. So this really does minimise normal tissues as much as possible, spreads the damage over a wide area, but has as much radiation as possible focused upon the tumour. And that concept can be taken a step further with gamma knife or stereotactic radiosurgery, and this is originally was set up with a series of cobalt-60 sources, all pointing towards a single focal point. And this was originally used for brain tumours, where this clamp is placed on the patient, the location of the tumour very carefully identified, this drilled into the patient's skull. You then attach the cobalt-60 sources for a certain period of time, and that will irradiate just that point within the patient's brain, and all of the other parts of the brain will receive just a fraction of that dose of radiation. And each of these little marks on here represent a single cobalt-60 source, but they're all pointing towards the patient's brain, not that way. Now also we're thinking about brain tumours. The most important thing about brain tumours when you're doing radiotherapy is not damaging structures, and this is where proton beam therapy comes in. So you might have heard about proton beam therapy in the media quite a bit. There's a couple of centres. There's one at Christie's in Manchester, there's one at Clatterbridge, which is soon to close, which is going to be a bit of a disaster, we think. Proton beam therapy is used primarily for childhood brain cancers where you really don't want to damage the child's brain. It's used for tumours that sit on near the spinal cord, because you don't want to irradiate the spinal cord, because that can cause paralysis and damage to the spinal cord. And here in Sheffield, where we've got a specialist ocular melanoma group, a lot of the patients go for proton beam therapy for their ocular melanoma treatment. So you saw plaque brachytherapy earlier. Some patients will go for proton beam therapy instead. If the tumour sat right on the optic nerve, then proton beam therapy, for reasons which you'll see shortly, may be more appropriate. And the way it works is you fire a beam of protons at the patient, and depending on the depth of the tissue, that determines how fast the protons travel, and when the protons reach a certain speed, they interact with tissue. So they enter the body fast, they have a relatively low rate of interacting with tissue, but then as they slow down, they interact with tissue. So, and this has shown the degree of ionization. So as they enter the body at a shallow depth, they don't really do too much damage, and then suddenly there's a sharp uptake of ionization at a specific peak, at this point exactly 30 millimeters of depth. So let's say 31 to 27 millimeters of depth are getting good effective irradiation. Now the nice thing about proton beams is you can tune them so that you can fire them in at, in this case, 62 mega electron volts, and you will irradiate 30 millimeters incredibly well. That's 30 millimeters of tissue depth, but everything beyond 33 millimeters doesn't get irradiated because all the photons are being absorbed by the tissue and none of them are exiting beyond or penetrating beyond 33 millimeters in this case. And then you can just fire a whole range of different energies of photons, give a fractionated dose to irradiate an entire tumour. And this is shown here, and it shows how different it is to X-rays. So if you've got a tumour sat in your spinal cord, you irradiate from this direction, irradiate from this direction, and maybe from this direction, a lot of those are going to hit the spinal cord here, and that's going to cause spinal cord damage. That's not what we want to do. If you use proton beams, we can fire protons from this angle and tune them so that the protons going here will only go this depth and no further, and then fire them down this line and they'll only go to this depth and no further. This is your tumour here. And then fire them at a higher energy and they'll go to this depth, and then repeat the process from different directions. So you never fire photons that penetrate deep enough to hit the spinal cord. So we do this using what we call a spread out Bragg peak. This is called the Bragg peak effect. This thing here is the Bragg peak effect, no doubt discovered by someone called Bragg. So what we can do is give a radiate. Let's say this is the tissue depth, so this is healthy tissue, this is your tumour, this is healthy tissue behind it, this could be your spinal cord. So you fire in protons, fire in protons at lots of different energies so that only this region gets irradiated, this region never gets irradiated, and the healthy tissue in front of the tumour gets a lower dose of radiation than the tumour itself. So we can vary the proton beam from 70 to 250 MeV, and that can target at the lower end a shallow tumour, and at the high end a very deep tumour. But even that, what we'd do is have an MEV that basically means that everything beyond the tumour never gets any radiation. So just for a little bit of context to let you know what sort of research that I do, I'm currently using gold nanoparticles as potential radiosensitizers in little mini tumours that I grow in the lab. So gold nanoparticles are little clusters of gold atoms, maybe 1,000 gold atoms all stuck together. And the beauty of gold is when they are hit by a photon, they often give off loads and loads of damaging electrons. So one photon could hit a gold nanoparticle, it can resonate and then give off lots of local electrons, and those local electrons can cause more damage. So if the photon hits the gold, it can cause more damage than the photon passing through the cell and splitting the odd water molecule. So I'm using this as a radiosensitizer with the aim of moving this peak here down in this direction. So I'm hoping to be able to give to achieve 100% tumour cell kill. I'm hoping to give a lower dose of radiation in the presence of these gold nanoparticles, which themselves are pretty chemically inert. Now, a lot of those hydroxyl ions and radicals that are given off are mopped up by natural antioxidant proteins and natural antioxidant chemicals that are created within cells. So the other part of the research that I'm doing is assessing drugs that might prevent radioresistance occurring. So some tumours seem to be naturally resistant to radiotherapy. If you can give agents that block these proteins that mop up reactive oxygen species, then that might help. So I'm blocking a particular pathway which is known to induce the antioxidant response and is known to be associated with radio resistance. I'm blocking that pathway in these little mini tumours that I grow in the lab and trying to see if that is a radiosensitizing mechanism. Finally, we know that some cancers overexpress, lots of cancers are hypoxic, got low levels of oxygen, and we also know that in the presence of low oxygen, radiotherapy doesn't work as well. So I'm looking at strategies of driving the cancer cells to sort of be less hypoxic and see if that can radiosensitize as well. Okay, that's everything from me. Just to let you know, this lecture was supposed to be given by a radiotherapist. Unfortunately, that wasn't available this year due to various reasons, but hopefully I've explained it in the way that the qualified radiotherapist would have done that. Also on this YouTube channel you find other videos that I've done, not just for the topic site, but also for subjects that you will come across in your second year and final year. So feel free to have a look around the YouTube site looking at other videos that might be relevant for your future studies, and just have a good look around.